As discussed previously, we went over three different ways to solve linear problems in transport phenomena. And so I wanted to code up an example to show you what this looks like. And so here's a little demo of what it looks like. And I'll just briefly go through the code. I'm going to have another video where I go more in depth in the code. I'll just tell you the parts. Here's the module part. Here's the finite Fourier transform part. Here's where we create the similarity solution. And this is probably the most complex part where we create a PDE solver using method of lines. And you can pause and read that. It's not the most optimized, but it gets the job done. So, and here's just like some slider stuff because I want to create a visualization for it. And here's the update function, and it plots it as well. Also, here, so here's the stuff that updates and checks for updates when we create the solution. So I'll just go into the graph and show you what's going on. So first, I just wanted to plot the similarity solution and the numerical solution. And it can be thought of as the numerical solution is pretty close to the real solution of what this problem would look like. And the real solution would just be FFT in this case. But uh, here we have the x domain on the x-axis, and here we have this non-dimensional theta, which is representative of the concentration. And so we see that at early times that the numerical solution is equal to exactly the similarity solution. And this makes sense because for very short times, the domain is approximately infinite for really small times because it can't feel the effect of the other boundary just yet. But if we move through time, and we'll see, so it's probably even imperceptible, but even at a non-dimensional time of 0.04, you don't see variation. But if we move a little bit, we can see it starts to deviate from the numerical solution. And we can see that in later times, it approaches it approaches very far away from the numerical solution. The numerical solution is just a line in steady state. But we can focus a little bit on the transition here. But you can see as we go backwards in time that it starts to deviate at this end here. It's starting to feel the effects of the boundary. But if we want to plot it against FFT, I have to rerun the cell. And so this is what it looks like in comparison to the FFT solution. And so the number of terms we add does affect how good the solution is. And so here we just have two terms, and we can see that this solution is not very good. So if we increase the number of solutions, you can see it approaches the true numerical solution pretty closely. If we add even more terms, we're getting there. But I think around like 7 terms, you can't even notice the difference. This interestingly, this only really applies at short times because if we go to really long times, we can see that it doesn't matter as much. And that's because of the exponential part of the finite Fourier transform. But we can see that the finite Fourier transform is actually very close to the numerical solution here. Well, it is basically the numerical solution. So I just wanted to give a little bit of demo and show you guys what it looks like as we change time. And we can see that it starts to drift apart here. And so in my next video, I'll go through what the code and like what we have to think about when we're developing the code kind of looks like.